Okay, welcome back, folks. So last time we got started on the first few steps of what's involved with indexing in OpenSearch. As you may recall, we started with REST index action, which was the REST HTTP endpoint. We saw how that parses the JSON request. Actually, I can open that up so we can follow along. So yeah, so we start from REST index action. It parsed the REST request into an index request, taking the various parameters. Then after we well, that ends up routing to an internal client, and we saw how that client is actually a node client. And so so specifically, which actually I think it was client base or some kind of client.
I guess abstract client, no?
Abstract client, that's the one. Thank you. Yeah, so abstract client. Yeah, so we went to its index method, which is bound to the index action, the instance of index action. And we took a little detour through the action registry and saw that, on node startup, these actions get linked to what are called transport actions. And so that's where we got to transport index action, which, as we mentioned, is marked deprecated, but probably isn't going to go away for the foreseeable future. So yeah, we're probably, just going to keep using this. But transport index action, of course, extends transport single item bulk write action, where index actions and delete actions both get translated into bulk actions with a single element. And this one takes care of wrapping the request in a bulk request and unwrapping. Wrapping the request here and unwrapping the single item bulk response back into the appropriate type. But that really, the work happens in bulk action, and we saw that the bulk action is of type transport bulk action. So that's where we left off. In transport bulk action, we were in this do internal execute method, which takes care of sending the bulk action to ingest pipelines if applicable. So that was here. And then we got into if auto create indices is enabled, or even if it's disabled, but there's a system index mentioned in the bulk request, then there is a rule saying that system indices can always be auto created even if that setting's turned off, because otherwise some plugins might break because they expect to be able to auto create indices. So then when the auto create index calls complete, there's this repeated pattern where we're actually going to see something like this again, where something gets broadcast out to we dispatch multiple requests. In this case, it's multiple create index requests. We set up an atomic integer indicating how many outstanding requests there are. And as soon as the number of outstanding requests hits 0, we do something else. We execute essentially a final callback, where in this case, the final callback does execute bulk. Well, and there are a couple ways that the number of outstanding requests can hit 0. One is that the last one was successful, or the last one failed. And in either case, we do want to, execute the callback. So in this case, executing that callback is saying, okay, well, now it's time to actually execute the bulk request. Well, and how do we execute the bulk request? This ends up the real work of executing the bulk request. With all this time that we've spent in transport bulk action already, nope, this isn't the thing that does the actual bulk operation. That's something called bulk operation, which is an inner class. So bulk operation is right here. Actually, as we see, it extends this class called action runnable. Action runnable is used a fair bit within OpenSearch. Let's take a very short detour into what action runnable is. Well, let's read the Java doc. So base class for runnables that need to call action listener on failure in case an uncaught exception or error is thrown while the actual action is run. So yeah, essentially it just kind of it kind of delegates to what it uses an actual runnable, right? And then yeah, the key piece from what I remember. So where is the exception handling? It's not actually inherited. Ah, yes, yeah. So this is the somewhat interesting one. Yeah, so we wrap a regular, well, yeah, we don't wrap a regular runnable. We extend the regular runnable interface to say like, okay, when you run, I want these semantics, right? So if there's an exception, I want you to delegate to the on failure method, and if you succeed, I want you to call this on after, which, if I recall correctly, interestingly, we don't actually extend the on. Oh yeah, because the on after is in a finally block, so it gets called no matter what. Yeah, we want to be able to distinguish between the runnable being successful here, where we call back to a listener and say, on response null. Yeah, because it's a runnable, it doesn't actually have a response, right? It's not a callable that returns something. Yeah, so in the successful case, it's what we'll do. Yeah, oh yes, and of course that, yeah, the instance of action runnable has this on failure method that delegates to the listener on failure, right? So, and that's what gets called if an exception's run. Cool. So, yep, basically just an exception-friendly listening runnable. So, OpenSearch very, makes extensive use of this callback mechanism. So, yeah, in this case, the bulk operation does have this action listener. So, if an exception is thrown anywhere in this do run method, that listener will be notified. So that's good, because otherwise your client would just hang forever if an exception was thrown, right? Because if you don't notify your listener, it means you never reply on your network channel. So let's get into the bulk of this do run method, because as we saw, because this bulk operation extends action, the call to run really just delegates to this do run. So could we run a bulk operation? So first thing we need to do is get the cluster state. And one of the reasons we have to do that is there may be a cluster block in place. So we just, right, so this is if there is a cluster level write block, then yeah, we'll say, nope, you cannot write right now. So yeah, this is just kind of a safety mechanism to keep from overloading the cluster. And yeah, it'll try scheduling a retry, to try a little bit later. So we don't need to get into that right now, but yeah, good to know it's there. So the other thing we have to do is, okay, so now we've got this bulk operation or this bulk request that may consist of multiple operations. If we came from an index request, it's actually just one, but we don't know that here in bulk. So we iterate through each of the individual requests, the individual index delete, well, yeah, index requests or delete requests, doc write requests, ultimately. So we skip null operations. There when we were auto creating indices, if we failed to create an index, the requests all got nulled out because like, oh, if the auto create failed, then we can't actually proceed with the doc write requests. Well, this is a nicely named method. This add failure if requires alias and alias is missing. So if the operation requires an alias and the alias is missing, then we'll skip it and we'll append a failure to the bulk response. Similarly, if the index is unavailable, then yeah, we'll similarly skip it and we'll error out the request. And if none of those happen, we'll call this concrete indices resolve if absent. So concrete indices here, its own class called concrete indices. So the presence of this resolve if absent, I'm assuming this is essentially a fancy way of saying compute if absent, because as we can see here, concrete indices is backed by a map indices. So if we look at resolve if absent, sure enough, we try to get if the concrete index is null. We use what's called the index name expression resolver and ask for its concrete write index. So I'm more familiar with the index name expression resolver from the search side because I mostly work more on the search side than on the indexing side. But in terms of why there's a dedicated concrete write index method, this would be because there's a similar sort of thing on the search side where I believe it's called concrete indices, where you could pass in what looks like an index name but may actually be an index alias. And that's because on the search side, a single index alias can actually map to multiple indices, right? So you can have an alias called logs that actually points to the logs for this week, the logs for last week, the logs for the previous week, and maybe it has, I don't know, say a 4-week rolling window. And so on the search side of things, when I search for logs, I want to be able to search for these 4 weeks. On the right side, maybe I also want to be able to send my documents to an alias called logs. And what happens is every week when I roll over that alias, I update so that the right index becomes this week's index. So that's an alias can have multiple concrete search indices, but only one right index. So yeah, so this is essentially doing alias resolution. I guess it can also do pattern resolution, but I don't think you're allowed to do that because it would have to map to a single index. And so if you tried specifying a wildcard in your index name, it wouldn't resolve to a single index. So that clearly wouldn't work. Yeah, and of course, to avoid recomputing the index name resolution multiple times, we store in this map, and then next time around, if we see, say, the same alias, and say, okay, we don't have to do the lookup again. We can just reuse the same value that we computed previously. Cool. Let's go back to do run. So for each operation, we figured out what the actual index name is. Now, what do we have to do? So based on this concrete index name, we get back what's called an index abstraction. Now, this is because it may, yeah, as they call out here, the resolve absent method validates whether an operation is allowed in an index into a data stream, but this isn't done when the resolve is cached. So the validation needs to be performed here. Aha. So that resolve if absent kind of takes care of data streams, but if you have a data stream, I'm trying to recall with data streams. Oh, yes. So data streams only support create operations. You're not allowed to update a document that's been written to a data stream. That, yeah, it's only creates. So yeah, we if there's, what could happen here is that, a data stream has a backing index. And so, yeah, if you're trying to write to the backing index directly, and that's where we ask for the index abstraction parent data stream, right? So, yeah, if we're trying to write into the backing index and it's of type create, then yeah, or sorry, it's not of type create, then yeah, we should throw an exception. Saying nope, you can't do that. And note that if that's the case, because this is within the for loop, this particular illegal argument exception won't error out just that bulk operation. It'll actually error out the full bulk request because it's saying, whoa, 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 this bulk request, you're trying to do something illegal. Let's stop it. So, that's an interesting distinction as to whether it fails at the operation, like the bulk operation level, or at the individual doc write request. So now let's get into the processing of the individual doc write request. So if remember how we took our index request and we wrapped it up inside a bulk request, as a single item bulk request. Well, now as we're iterating through the individual items, if the operation is create or index, we actually turn it back into an index request. So we unwrap it. But this, we're still reusing code, right? Because this could be multiple index requests in the bulk request. So, we get back the index metadata for this specific concrete index that we're indexing into. And so we have to pull out a couple of pieces of information. So we've got the version that the index was created with. We'll see why that's relevant. Then, yeah, we resolve the routing. So let's dip into that. So metadata.resolve write index routing. So here we have the index. we have a routing string that may be a property on the index request. So I think we saw in the case of the Rust index request, that you can, as a user, you could specify, a routing request at indexing time. So you can say, I want this index request to be routed according to this string. And this is useful. By default, documents get indexed according to the hash of their doc ID. So it's just, do a hash function on the doc ID, and based on that, choose which shard it lands on. And the goal is generally to balance documents across shards. So the hash function is giving you a fairly uniform distribution, ideally. So instead, what you can do is you can say, no. I know something about this document. I have some property of this document, and I want it to be routed according to that property. And, because later on when I search for it, I'm gonna know, hey, I only want to search for documents with this property or these properties. And so when you search, you don't have to pan out to all shards. You can target the specific shards that have some string attribute that you like. But in the general case, because later on you have to be able to find the documents, I believe here. So by the normal situation is that routing is null, right? So let's see what happens. So when this method's called, we can be given an alias or an index. Recall here, I think actually at this point, yeah, in the index request, did we overwrite this with the concrete index? We have the doc, right? Yes. Oh, no. No. We got the metadata for the concrete index, but we didn't update the index specified in the index request. So, yeah, at this point, we may actually still be dealing with an alias. So, this alias or index, where again, we have to use the indices lookup to resolve what could be an alias. So if the result's null, or if the result is not alias, oh, okay, then this is where we just return the original routing, which may still be null. Okay, so this isn't where we're computing the routing. This is still all about alias resolution. Right, so oh yeah. Oh yeah, I forgot about this. That yes, an alias can actually specify, can override the routing of of index requests. Yeah, so that's why this method exists. That yes, an alias is allowed to override the parent routing. Got it. Okay. Okay. Yep. That's so yeah, that explains what's happening here. So where were we? Cool. So we resolved the routing. So again, this is related to alias resolution. And then we process. Oh, interesting. So remember I said we figure out the version that in this case this is the OpenSearch version that an index was created with. I said we'll see what's done with that. Well, the answer is nothing. Absolutely nothing. That this is an unused variable. So yeah, I assume this is historical. That once upon a time, that maybe there was some kind of check to see, oh, maybe there was once upon a time, there may have been something you could do with an index request that was added later. And so therefore we needed to say, oh, add this thing if we're dealing with a newer index. But if it's an older index that didn't expect this kind of thing, don't add it. So yeah, we do have a number of things like that for backwards compatibility. So, but we only extend that backwards compatibility back one major version. So I'm just going to check what's the history here. I'm just kind of wondering if this is something. I'm just going to hover over these. Oh, okay. Yep. So type. Yes. Uh, yeah. So once upon a time, there used to be this concept of types where you had to specify a document type within an index, where a single index could hold multiple types of documents. And so, yeah, there was, deprecating types actually spanned multiple versions where types were deprecated a long while back. And then people were given at least a major version to stop using them. But then, there was still the next major version. You could still specify types if you were writing to an old index. So the idea was, you know, I believe in OpenSearch 1.x, we said that, yeah, if you were upgrading, I think from Elasticsearch 6.x, if you had an index that was created in 6.x, you were still allowed to use types because that index had been created with types. But that if you were using an index created in Elasticsearch 7 or OpenSearch 1, you could not specify types because they had been marked for removal. Okay, so this is why the index created version is passed in. Technically, now in OpenSearch 2 and OpenSearch 3, especially in OpenSearch 3, we could probably remove this, right? Because it's no longer relevant. Anyway, okay. So what does process do? Well, we go through, make sure that we have the mapping metadata, do a double check to see that we have the routing info. Oh, if routing is required. So you can specify in your mapping that you expect users to provide this routing, to supply this routing information, which is good. If you do have an index that's using custom routing, you generally do want to use custom routing throughout. So yeah, we check the ID field, make sure that it's never an empty string. It can be null, in which case this is where we auto-generate an ID. We record the timestamp of when we auto-generated it. And then, yeah, this one is just generating a UUID, a globally unique identifier. Yeah, so, but the disappointing thing here is, so we called this method called process, but we haven't actually done the index request. This is ultimately, I wouldn't call this prepare, I don't think. I think I would call it something more, or sorry, I wouldn't call this process. I would call it more like something like prepare, right? That we're not actually processing the index operation or the index request yet. We're just kind of, well, really the only functional change that we're doing here is we're generating IDs. Maybe once upon a time we did more back when we still had types. But yeah, so okay. So we're just generating the ID. So So yeah, this method here, or sorry, this switch case seems to be like depending on what type of sub request this is underneath the bulk request. We're really just doing some validation, some preparation. Similarly with update actions, yeah, we have to validate routing. Delete actions, we're also setting up the routing. We, if any of these steps fails, right? So we've got parse exception, illegal argument exception, routing missing. Oh, yeah. Sorry, I had said previously here, like, oh, if we throw this illegal argument exception, then we'll fail the whole bulk request. That's not true because we catch it down here. So we will just error out that individual item. So please disregard what I said earlier. I was wrong. So now, okay, so we've taken care of some validation. We've done some we've set up the routing if necessary. Well, routing may still be null if we're not using custom routing. So again, so we iterate through. I like how this says first go over all the requests, when in fact we just went over all the requests up here. So we could update this to say second go over all the requests. And so we need to resolve the operations to the relevant shard IDs, right? And so that's where computing custom routing, if it was required, is useful. But otherwise, yeah, we compute these shard IDs down here, right? So don't forget that we've resolved all the concrete indices for each request. We did that up there. If we call over here to say, okay, well, for this request, given this ID and its possible custom routing, right? So in the default case, the ID, we've figured it out. It was either passed in or we auto-generated it in that process method. We may have custom routing, but normally we don't. Normally we just let OpenSearch figure out the routing itself. And so here, right? So we're passing in the ID, which is definitely not null, and the routing, which may be null and is null in the default case. So yeah. So this calls into this generate shard ID that based on the index metadata, the ID and the routing. So if the routing is null, then we say, okay, we are going to route according to the ID. Otherwise, we're going to route according to the custom routing. So this is what I was alluding to before. That by default, we route according to the ID, but that you can override that. So yeah, is routing partitioned indexed? I'm curious what this means. Routing partition size. So if I recall correctly, in order to support index splitting, so you can, or shard splitting, I believe that's tied in. Yeah. So you can specify. So let's say you have, I don't know, like 10 shards in your index. You can actually specify that for routing purposes, you want to have, I don't know, 1,000 shards. And what will end up happening is that your 1,000 routing shards will get mapped to your 10 physical shards in a nice, consistent way. And the reason why you do that is because maybe right now you have 10 shards, but in future you want to be able to go to 20. And as long as your physical shard count is as long as your virtual or routing shard count is divisible by your physical shard count, there's a way to split up, to reshard, move things around, and kind of keep things consistent. So, yeah, that's what this routing shard count or routing num shards, the routing factor and the routing partition size, and factoring into. So, okay. So yeah, so this is where we may have to compute a so-called partition offset. If now the partition offset is always based on the ID, not based on the custom routing. So that's relevant. And then yeah, otherwise, yeah, we calculate the so-called scaled shard ID, where, yeah, well, so we do the floor mod. Okay, yeah. So with this routing factor, so they say we don't use index metadata get number of shards since the index might have been shrunk such that we need to use the size of the original index to hash documents. Ah, of course, yes. So with this custom, sorry, not custom routing, but this partition routing, right, where you can kind of overscale the number of shards. Yeah, as you grow and shrink your index in terms of physical shards, you have to do all of your calculations in terms of the routing number of shards. And I believe it's this routing factor that is the number of routing shards divided by the number of physical shards. And so, yeah, this is where we have to hash according to the big number, but then route things, sorry, scale that down to the number of physical shards. Cool. So yeah, this is how we've figured out the shard ID for each bulk operation. So we essentially do a group by, right? So we build up this map and we say, okay, so let's map each bulk item request to a shard ID, right? So we've iterated through all, here we've iterated through all the bulk requests. We've said, okay, you're going to hit this shard, you're going to hit this shard, because we're going to send a network request to each shard. We're going to get into that shortly. We compute statistics. So I could be mistaken. I think this bit here is actually relatively new. Yeah. Yeah. So this was previously we didn't have doc statistics. So yeah, Rohit added this just last year. So yeah, this is because, of course, when you send a bulk request consisting of multiple underlying requests, a mildly annoying thing is that if any of them fail, sorry, unless all of them fail, if some of them succeed, we return a 200 okay status code. But yeah, it is nice to keep track of like, hey, of our bulk requests, how many of the underlying requests are failing and what are they failing with, right? Are they failing with validation errors that, so 4xx responses, or are they failing with server errors where, as folks who operate an open source service, we like to know when we're failing. So, yep, this adds counters for that. So that's nice. Okay, so we have one of these counters. So you may recall with the create indices, with the auto creating of indices previously, we kept track of how many outstanding requests we had. So we're going to do a similar sort of thing here. So that's what this atomic integer is for. We're going to iterate through the map. So when we enter this, on each iteration here, we have one shard, potentially multiple operations, right? So that's where we may have multiple operations going to the same shard. And so we construct what's called a bulk shard request, which is kind of like the bulk request that we've been iterating through. But that this is going to operate at the shard level. So we construct the shard request based on the current bulk request. This is a pattern that does happen in OpenSearch a few times. That you have a coordinator level request. So the request that operates on a single node. So request comes in, a single node receives it. That node functions as the coordinator for the overall client request. But then that coordinator says, my job is just to delegate this to the underlying index shards. And so I'm going to take this coordinator level request and construct a series of shard level requests. And those shard level requests end up copying stuff from the coordinator level request. So that's what's happening here. Later on, when we get into search, not today, that'll be a different video. So we'll see a very similar thing over there where there's an incoming search request which gets mapped to a series of shard search requests as the request fans out to multiple shards for searching. So here we're constructing our bulk shard requests. We do want to link the bulk shard requests through the task API. We want to say that these bulk shard requests, which will be their own networking tasks, are associated with this top level coordinator task. This is relevant for task cancellation. So this will say if we cancel the overall bulk request, we should cancel these individual shard level requests. I'm a little bit curious as to what this routed based on cluster version means. Just gonna check, see what this is. I'm not familiar with this. Sets the minimum version of the cluster state that is required on the next node before we redirect to another primary, used to prevent redirect loops. See also this transport replication action, reroute phase, do run. Yeah, okay. Oh, so this is the cluster state version. So this is not based on. Oh, okay. Okay. Yeah, I think I see what's happening here. So cluster state, is sort of the global state of, among other things, what shards live where on the cluster. So I suspect that this is basically a way of providing a somewhat consistent view of the world as to like saying, hey, where is the primary for the shard? So it's saying, I'm routing this according to where the primary was at this particular moment in time in the cluster state. I believe that's because between when the coordinator receives the request and when it gets forwarded along to the node that it thinks is the primary may have changed. So that receiving node could potentially say, oh, no, the primary is not here. Instead, this request should go somewhere else. And you could imagine a scenario where, based on the cluster state on multiple nodes being out of sync, you could imagine a scenario where a request basically keeps getting handed off between nodes saying like, nope, it's not me, it's over there. And somebody else is saying, nope, it's not me, it's over there. And yeah, that essentially the request keeps getting passed around. So yeah, this is saying, as of this version, I believe that the routing should be this. So yeah, so we may get into that forwarding later on. Okay, so kind of skimming down through what. Okay, so here's where we actually execute the shard level request. So we have a so-called shard bulk action we call execute. Recall that pattern that I mentioned before with the counters. So if the shard level request is successful, we decrement the counter, and if it's the last one, we call the finish method. And similarly with the on failure, again, as if a request finishes, then yeah, we decrement the number of outstanding requests, whether it's success, it finishes on success or on failure. It's still one less outstanding request. If the number of outstanding requests hits 0, we do the final callback. That we say, okay, we're going to return to the listener a bulk response that we've constructed, right? So we've got our responses, which we have captured in an atomic array somewhere. Where did we set up the responses? Okay, yeah. So it's part of the bulk operation. So this is a so-called atomic array. Yeah, which is an internal class to OpenSearch, where mostly it's a wrapper around atomic reference array. So we see a very similar pattern on the search side as well, that we fan out shard requests, search shard requests, and each one we capture the response in this atomic array so that we can coalesce them in the callback. So yeah, we take these responses and we send them back. So this is something, the fact that this the method that calls the callback is called finish him, I believe is a Mortal Kombat reference. This is sort of a long-standing joke that appears a few places in the code base. Yeah, it's, if we look for occurrences of finish him, 46 matches across 11 files. Well, of course, yeah, so these 11 files are the 11 distinct places where, yeah, there's a callback. Well, again, they're all pretty much things that fan out to multiple shards. And when the last one, as the last one finishes, oh, this on phase done. Yeah, somebody called it on phase done because that was a more descriptive name. But somebody left a comment saying this should also be known as finish him. So anyway, yep. Yeah. Nice little Mortal Kombat reference. Yeah. Okay. So the real interesting part is the shard bulk action. So we're calling execute here, which, as you may recall, execute is actually just a generic transport action thing where the real work happens in the do execute method. So we're going to have to go to, what is it called? Transport shard bulk action. So this one, so we don't have a do execute method here, right? So sort of hovering through the structure, I don't have do execute. I believe that comes from one of the parent classes. So transport write, so transport shard bulk action extends transport write action. So this can include all kinds of write type operations. So index delete shard bulk allows performing async actions, e.g. refresh after performing write operations. And this extends transport replication action. And this is the thing that has the do execute. So the do execute will go through a reroute phase, just checking to see what things override do execute. It's like, okay, publish checkpoint, retention lease background sync, retention lease sync action, transport resynced replication action. So none of those are relevant to what we're doing right now, which is we're just indexing documents. But yeah, so we have the task, the request, whether this is initiated by a node client, which by default is true when we call this from do execute. So we're going to call this reroute phase. So I could be mistaken, but recall in transport bulk action, we didn't do anything regarding primaries, right? We resolve things to a shard ID. Let's jump back here. So our shard bulk action is resolved to a shard ID, but let's look at shard ID. So shard ID is essentially just saying, for this index, I've got some shard, right? And then otherwise, yeah, just the early materialized hash code. So we don't have to redo that computation. So this is essentially saying like, index logs this date, shard number 5, right? But it's not making a distinction between primary and replica, right? So I believe that this reroute phase, among other things, will have to end up rerouting to the primary, right? Because that's a step that's got to happen somewhere. Yeah. Okay. See, so this is where in the reroute phase, in its do run. So again, we look at the index metadata. Oh, we were saying that we want to avoid that rerouting loop. Well, the reason for that, well, and that's, yeah, the routed based on cluster version. So this is the version of the cluster state, and we're saying, hey, once we hit this point, the cluster state must be at least as new as the cluster state that on the coordinating node, right? So yeah, and otherwise we retry. So I assume this retry will say, okay, well maybe we can try again after we've got a new cluster state, I guess. Oh, we're at 8 o'clock. I think we might leave it here. So we still haven't gotten off the coordinator node yet. Yeah, we've traced down through more setup for the indexing request, but we haven't actually fired off the request to the primary shard, or the primary copy of a given shard. We have resolved each indexing request in our bulk request to which shard it goes to, and we're just about to get to the step where we figure out where the primary shards are, and we're just down here. We're very close to where we actually fire off the request to the primary. But I think I'll leave that for next time. I will try to schedule that for later this week. I would like to wrap up indexing soon so that we can move on to how search works. So yeah, thank you all, and yeah, I'll see you next time.
Thanks a lot, Michael.
Thanks.
Thanks a lot.
Thank you.
Thank you. me stop recording.